Hey, how you doing? Let's see, is this, there we go. So I'm really happy to be here. I got a call from Navid. He told me what they're trying to accomplish with TKS, and I'm very impressed by it. I think I've met some amazing young people here today. Curious, passionate, smart, surprisingly smart. And I'm going to tell you a little bit about my own story, but I'm going to tell you about one of the most amazing features of our universe that's often, I see people go to school, high school, college, and they don't learn about some of the deepest understandings, some of the most profound mysteries that we've uncovered as a civilization, and sometimes never learn it. And everybody should know these things because they've been around for over 100 years. So you'll see the title of my presentation. It's Accessing Vast Untapped Resources. So first I want to point out, you should understand that most of the physical universe is invisible to you, right? So right now there's magnetic fields passing through your bodies and through this room. You would know that if you took out a compass and saw the compass needle moving. There's something invisible. You all have cell phones, and somehow signals from across space travel to this little phone and end up in a voice that you listen to, but that's invisible to you too. You can't see the curvature of space and time that keeps you near the Earth that Einstein described. So most of the physical universe is you're completely unaware of with your senses. And it's only through building kind of advanced instruments that we can peer into these invisible realms. And what you see when you look in those invisible realms is staggering and surprising and more mysterious and magical than anything you can imagine. And so I'm going to talk about a kind of technology that's looking into parts of the universe that are completely inaccessible to you and what it might allow for us as a civilization. Now, one thing I think that you just heard about synthetic biology, there's something really important that everyone at this conference, I hope, comes away with. You live in a world right now where civilization itself is at risk if we continue to behave the way we have. We know that there's destruction of the biosphere, of the planet, social injustice everywhere. Most of our institutions on Earth are run very suboptimally and subject to severe crashes. And it's important when you get into technology. I see a lot of people, technologists, get excited about something because it's interesting and because you can get a good job. But at the end of the day, I think a really important question you ask yourself, even at your young ages, is what kind of world do you want to live in? I'll tell you what kind of world I want to live in, and I started thinking this way when I was really young. That's the world I want to live in. So for those of you who are Star Trek fans, Gene Roddenberry had a vision of a world. You see people from all different parts of the world. You have Russians and women, men, aliens, all working together, going on a grand journey of exploration throughout the universe. But one thing that Star Trek did for me when I was young, they talked about a time in human history. They talked about what they called our technological adolescence, where our cleverness was outstripping our wisdom, and that we almost destroyed ourselves. Whether it's the brink of nuclear war, whether it's environmental catastrophe because of our petty jealousies and fears, or our consumption, that could do us in as a civilization. And most species on this planet have come and gone, and we could be one of those. Or, if we get smart enough, we talked about a lot of potential solutions to big problems at this conference, but it's not just smart, and it's not just technical solution. The other thing that we have to have as a civilization is ethics. So you have to ask yourself, if you're working on a project, why am I working on this project? What sort of worldview does it support? Is it a good idea? There's a lot of conversations now going on about whether it's synthetic biology or AI and whether they're a good idea. What are the ethics surrounding that? And this is supremely important when you're a technologist, not to just do things because you can or because it's interesting or because you get paid a lot of money. You should have a worldview in mind, and that's mine. So something to understand about the civilization we've built a civilization of staggering complexity. So this is a picture of, the United States and Mexico, Central America from space. And you can see all this stuff lit up using enormous energy resources. And what's happened with all of this complexity is the complexity itself has generated problems beyond our understanding. If you look at every area of human endeavor, right? So what this represents is each one of these little points. Let's say I look at a financial network. Each one of those could be a company or it could be a stock. And maybe there's hundreds or thousands of them. They interact in very complex ways. Whether it's the way that you're distributing energy on the electrical grid, whether it's social networks, whether it's the defense network where you have systems of satellites and sensors going through millions of lines of code. What happens when you have very complex systems like this is that right now, we don't have the ability to build good models. So you try to build a model of the world, whether it's a financial world or a defense network world or an energy distribution network or an ecosystem of the Earth, like the climate. And right now, with our grandest supercomputers, we can't build models that allow us to understand how those different objects or entities interact and what might happen. We don't know the best way to design these systems. We don't know how to predict outcomes. In fact, at D-Wave, we're working with a lot of companies that understand this very well. So, say people at Lockheed Martin, you say, well, you look at a defense network or a flight control system on a spacecraft. You could have some birds that flew in front of a radar and maybe a satellite that had an electrical circuit that burned up a little bit, and some of these signals come through millions of lines of code that are very complicated, and you get, let's launch on Russia, right? Because of a mistake. You can have financial institutions where certain combination of stocks moving around in just the right way cause massive crash that you could never predict because these systems are completely beyond our ability to model. Why? And even with all this stuff, by the way, I call networked brains, that's everyone on the internet working together, massive Google data centers. We're now generating data, prodigious amounts of big data you hear about all the time. Neural nets, we have machines that learn, that can look at that data, that's smarter than any human and looks at all these multivariable problems. And even with all that stuff, we can't model most of the complex systems that exist on Earth right now. I'm going to show you like a little graph. What this represents is, if you look at this bottom graph, there's a science called complexity theory that's just about this. How do we characterize complex systems? How can we try to understand them? There are problems when, let's say, you double the problem size, where it takes twice as long. And that's problems like you see this bottom line. They're called polynomial scaling problems. But the idea is, when you make the problems bigger, it doesn't take that much longer to solve them. So if you look on the y-axis, that's how long it takes to solve it, and the x-axis is how big the problem is. But these problems that I'm talking about, these large-scale complex systems in our civilization, even something like managing the healthcare system, you make the problem a little bit bigger, and it takes a lot longer to solve. And those are exponential problems, and that's most of the systems we have on Earth. And so, when you build these big giant supercomputers, as you add more and more processors, 2 processors, 3, 4, they might just get 2, 3, 4 times faster. So they're increasing linearly where the problems are blowing up exponentially. You'll never catch up. Even if you took all the atoms in the universe and built them into computers, you can't solve these complex problems. So what do? Is there any kind of phenomenon in the universe that we might be able to harness to solve some of the biggest problems we face as a civilization? Well, throughout human history, whenever we harnessed new resources, it led to dramatic increases in our capability as a species. These are some of the big ones, fire, agriculture, tool making, electricity, nuclear energy. And sometimes we don't make the best decisions. I go back to ethics. What did we do with E equals MC squared? We figured out how to make a little sun and put it on somebody's city. But there are some phenomena in nature that are staggering that we've known about for 100 years. that if we harness in the right way, we might be able to solve this problem of complexity. So in the early 20th century, in the early 1900s, some of you may have heard of something called quantum theory. So we had, prior to 1900, we had classical mechanics like Newton and electromagnetic theory, and people felt pretty smart, and they thought they knew a lot about the world and that we could describe everything. And in fact, they thought that atoms, a lot of you have seen this in your textbooks, where an atom is like, I've got a little nucleus and I got electrons going around in circles like a little moon orbiting a planet or the Earth orbiting the sun. So they have tried to apply the physics that we knew up to that point to microscopic objects like atoms and molecules. And what they found is it gave you the completely wrong answers. If you took classical physics like Newton's theories and electromagnetism, it predicted that atoms can't exist, that the electrons would spiral into the nucleus and release a bunch of radiation, and we knew that atoms did exist. So our best physicists of the day said something that wasn't true. So there had to be a radical change of ideas to explain what was going on at these microscopic scales. And the new theory was called quantum theory or quantum mechanics. And quantum mechanics allowed us to understand the world more precisely than any theory humans had ever devised. To this day, there's never been a single experiment that quantum mechanics didn't explain. The accuracy of the theory is unprecedented. It would be like, it's so accurate, let's say you want to know the distance across the United States. If you had something as accurate as quantum mechanics, it would be less than a human hair worth of accuracy from here to New York. So staggering accuracy. It gave rise to a revolution in a whole set of technologies. So we understand why the sun works, how fusion works, and maybe that could be a future energy supply for millions of years without screwing up the atmosphere. It gave rise to the semiconductor revolution. So all of your cell phones, everything that you use in your daily lives, all the computers, Silicon Valley was based on an understanding, the transistors, say, of something called a band gap in transistors, allowed for the semiconductor revolution. Biotech, DNA sequencing, nanotechnology, nuclear energy, all of this stuff that you take for granted was based on this understanding we got from quantum theory. But quantum theory, if you took it at face value, there's an equation there that's called the Schrödinger equation. If you take the equation seriously, it says some very strange things about the nature of reality. This is something called Schrödinger's cat. Schrödinger was the developer of that equation, and he said, well, if you take the equation seriously, there are conditions under which a cat could be alive and dead at the same time. That doesn't sound right. I've never seen that. So I'll tell you what happened back then. You know, after about 1930s, 40s, people said, the equations give us the right answer. We can calculate all this stuff, build technologies and lasers and semiconductors. And so I call it the shut up and calculate crowd. Forget about what it means, use it and do cool stuff. Now for a physicist, which is what I am, I want to know how the world is. Is the world that weird? Is there something wrong with this theory, but it kind of works for now? So I'll tell you some of the things that this theory says. One, there's something called quantum superposition. So what you see there is I have a particle, say at some position A, and it's going to go to position B. And what you're used to is if something goes from one place to another, it takes a well-defined trajectory through space. What this theory said, say for an electron, is that electron takes every possible path to get from one place to another. So everything that's possible for electron happens. You're not used to this in your daily life. I could choose to leave the stage or to stay, but could I leave the stage and stay at the same time? That doesn't seem rational, but this is what the theory said about how electrons behave. And in fact, if you don't assume this, you get the wrong answers from classical physics. Now, what would this allow you to do? Think about this. Let's say you had to get through a maze. What do? You start at one point in the maze, you try, you take the wrong path, you come back to the beginning, you keep trying to map it out, and it's going to take you a long time to find your way through that maze. But what if you could take every path simultaneously, and somehow you could talk to all of your other selves? One of you gets through the maze right away, tells everybody else how to get through, you solve the problem really quickly, right? Wouldn't that be amazing? There's another quantum effect called quantum tunneling. You'll have an object on one side of a wall that it can't get through, like you're a prisoner and there's big cement walls. And classically, if you're trapped in that prison, you're never going to see the light of day. I don't have enough energy to punch through the wall. But quantum mechanically, you can have a particle that disappears, appears on the other side of a barrier that it never passes through. Pretty weird. This happens all the time, and we have technologies based on this quantum tunneling effect. There's another effect called quantum entanglement. So I'll explain it this way. Imagine that I gave one of you some dice. And I'm from California. So I go back to California, you're in Toronto. And I say, I want you to roll your die 1,000 times and write down the results. So you write them down. You see, 2 through 12 randomly. And I see 2 through 12 randomly. But under the right conditions, which is called quantum entanglement, when we took our two lists of die rolls, 1,000 times out of 1,000, they'd be exactly the same. How could these dice know about each other and what was going to happen across space and time with no interaction between them, no signal? This is the kind of thing that this theory talked about. And all of these things have been seen in experiments for the last 100 years, and we're now building technologies based on them. In the case of superposition, so I'm going to talk to you more about quantum computing, but I'm going to give you quantum computing in a nutshell. If you remember nothing else, you can remember this example. So imagine there's the Library of Congress, and there's about, say, 50 million books. And I go into the library, I pick a book, and I put an X on one of the pages, and I put it back. Now I ask you, go to the library, find the X, you have 5 minutes. Well, you'd say, I don't even know if I want to start, because unless I'm very lucky, you go to the first book, flip through pages, go through the next one. It's going to take me many, many lifetimes. But if somehow I could be in 50 million places at once, or maybe 50 million parallel universes with libraries, in one of those universes, it's the first book that I pick, right? Okay. And then you've gotten the answer to something in seconds that would have taken you lifetimes. If this is true. Well, in 1957, this guy, Hugh Everett, he said, let's take quantum mechanics seriously. Some people said, yeah, it's weird, we don't quite understand it, but the equations work and we can build technology. He said, what this implies, and you can see there a piece of film that's splitting, if you take quantum mechanics seriously, what the equations tell you is that there's something called a multiverse, that the universe at certain points will split into these different alternatives, where in one universe one thing happens, in another universe something else happens, and under the right conditions they can actually talk to each other. That's called quantum interference. It's like all of your different selves in the maze, or all of your different selves looking for the X in the book. If somehow they could share information, you could do something really powerful, really quickly. So if you start thinking about these very complex problems I was talking about, what if I didn't just use this universe to do calculations, but somehow I could use these parallel branches of reality, and in those different branches I could do different things, or I could explore different possibilities, and somehow they could talk to each other so I could get information from a vast number of possibilities very quickly. That's, in essence, quantum computing. This guy over here, David Deutsch, is what I would call the father of quantum computing, and this is the way he describes it. Quantum computation is a distinctly new way of harnessing nature. First technology that allows useful tasks to be performed in collaboration between parallel universes. And I had a nice conversation with him at Oxford for 4 hours, and one of the most amazing, brilliant people I've met. So he had this idea for a quantum computer. A quantum computer is somehow, I can access these parallel streams of reality, have them talk to each other, and solve these immensely complex problems in seconds that might take the age of the universe on all of our classical computers. This idea for a while in the 80s was kind of this theoretical idea. It was interesting, but only a few people knew about it. And then this guy, Peter Shor at Bell Labs, did something that got everybody's attention. He said, okay, let's say you could do that. Let's say you could harness these parallel streams of reality and get somehow, and he applied that to a specific problem, which was factoring big numbers. So when you factor a number, say like 15, that's 5 times 3, right? But let's say I take a 200-digit number and I say, find the numbers, the prime numbers you multiply together to get that. Well, it turns out that if you have something like a 300-digit number, it would take a supercomputer the age of the universe to find the factors. So he said, yeah, but what if I could use these parallel streams of reality? And he wrote an algorithm using that idea, and he showed that instead of the age of the universe, maybe in a couple seconds or a few minutes, you could do that. And he published that paper. So what? What's the big deal about factoring? Some of you may know our most powerful data encryption method is something called RSA, and it uses the fact that it's hard to factor large numbers as a way of protecting information. And when he wrote that paper and said if you built this quantum computer, you could break RSA in seconds or minutes, guess who read that paper and freaked out? The NSA, DARPA, all of the security agencies, and they said if you built this machine, you could undermine our entire civilization by looking at everybody's bank accounts and looking at all the information that's going back and forth in international communications and all that. That's when the US government and others started financing this field seriously. Now, let's say you want to build one of these things. Some of you may have heard the word qubits, which means quantum bits. When you want to engineer a system, you want to build it out of the simplest components you can and make them robust. So imagine, I'm showing this little ring for a reason, but imagine I had a little ring, and instead of like a transistor that's on or off, this thing could somehow be in these 2 branches where it's a 1 in one branch and a 0 in the other, but it's the same physical object. And you can see there at the left, that represents 2 possibilities. Now you couple it to another ring that can be in 2 possibilities, and when you combine them, you get 4 possibilities. If you combine that with another ring, you get 8 possibilities. And what you'll see is as you add these objects that can be in 2 states at once, and you concatenate them, all of a sudden, the number of possibilities that this string of qubits can have grows exponentially, like 2 to the number of those objects. So you see a behavior of the number of branches you could explode exponentially, kind of like the problems we'd like to solve. And so this was this fascinating idea. And then also another thing that was going on in the 80s and 90s is people started to get exquisite control over microscopic systems like ions. So these guys at the National Institute of Science and Technology in Colorado, at NIST, they put a bunch of little ions, which are charged atoms. They were able to float them in these electromagnetic fields and interact with lasers, and they were able to do this, where each one of those, you see those little atoms with the laser, each one of those, they could put it in a state where there was like something called a magnetic spin that could be, if it was down, it was a 0, if it was up, it was a 1. They could put it in states where it was both simultaneously. They could build registers out of this, and they demonstrated all of this behavior I just told you about, superposition and entanglement, in those ion traps. And Dave Wineland won the Nobel Prize for this work a couple of years ago. Okay, so I'm telling you a crazy story, but I'm telling you a story that's at odds with your intuitions of the world. So I'm telling you the universe can branch and there can be all these parallel realities in which different things are happening. Well, you're built out of atoms, so how come you're not doing a bunch of stuff at once? You know, why can't I do my homework by having my other selves do, you know, different parts of my homework and combine it and take a few minutes instead of hours? People didn't understand this either until the 80s and 90s. And this is another bit of fantastic work that's called decoherence theory. So I'm going to try to say this in a prosaic way, which means I'm giving you a metaphor. Okay, so let's take the library example. Let's say all of your selves are looking at all the different books in the library. But let's say the windows to the library are wide open, like this. So one of your selves sees a movie theater, and it's like, oh, that's a movie I kind of wanted to see. The other self is kind of hungry and sees a cafe. I think I'll go get something to eat. Another self sees some of your friends and want to go hang out, okay? So the selves in the library that are coherent, which means they cohere to each other, they're working together, all of a sudden start getting pulled apart because they're interacting with something outside the library, the surrounding environment. And so it pulls the streams apart. One of you goes to the theater and hangs out with some friends, one gets something to eat, and all of a sudden, the computation or that problem solving falls apart because they no longer can talk to each other and share information. So then people realized when you have a little particle like an electron, if it's flying through this room, it hardly hits any air molecules or gets hit by any particles of radiation. It doesn't interact with its surroundings very much at all. But if I take this clicker, or I take me or you, this clicker right now is being assaulted by billions of atomic collisions from the air surrounding it. The light and radiation that's hitting this. It's in my hand that has atoms that's wiggling. All of those interactions with the outside is like the things outside the library that are pulling the streams apart. So, if you knew this, once this decoherence theory that said if we take all this environment and put it into the Schrodinger equation, it shows us that the branches separate. So what would you do immediately if you wanted to see all this weird stuff at the scale of our experience? What would you do in the library? Anybody? Yeah. Close the windows. If I shut all the windows and I keep you isolated from the environment, I might be able to see these quantum effects at macroscopic scales. So has this been done? Guess what? Sure has. In the year 2000, people at the University of Stony Brook, University of New York at Stony Brook, with predictions from Tony Leggett there, who made this prediction to do this experiment and won the Nobel Prize for his work, said, take this is a little ring of metal. And it's a superconducting metal, which means when I cool it, I can lose all the electrical resistance. So you take this little ring of metal. First, get rid of the air. So pump all the air out. Go to ultra-high vacuum. Then shield it from all the radiation. Then go to ultra-low temperatures so it's not connected to any surfaces that are wiggling. That's like closing all the windows, isolating this thing from its environment. And what they were able to achieve was they took that ring, they could put an electrical current that went clockwise, right? All the current went clockwise, and all the current went counterclockwise simultaneously in these two branches of reality. And because the windows were closed, you can see evidence of them talking to each other. So these two disparate, mutually exclusive possibilities exist, and they communicate information. And this was unequivocal experiment. It was, you can see there in the New York Times, they had Schrodinger's cat lives. Because Schrodinger's was a live and dead cat, then somehow they would know about each other. This is a ring that's in these two different states that know about each other. So when you see this, this was the basis of the technology. When I saw this result in 2000, I was working in a group that built rings like this for another reason. We were building what's called a superconducting digital technology. We wanted to build ultra-low energy computing, ultra-fast, ultra-low energy. Why? Because right now, the largest supercomputers, say Tehani at Oak Ridge, takes 12 megawatts to run. And people are talking about trying to do much better simulations of the atmosphere and the environment by building exascale computers, which could take 100 to 400 megawatts. One computer taking the energy of an entire city. So you'd have to build a nuclear reactor next to it or put it next to Niagara Falls just to run the computer. There's nowhere to plug them in. So I was working on a technology to build very low energy supercomputing. But it was based on rings like that that are called quantum interference devices. So I had the idea to build a company based on this idea. First, I want a big government contract, but I realized, I sat down and I said, look, I can take these rings that I make these qubits out of that can go into all these different realities, and I can use the superconducting technology I've been building already to interact with them, because the superconducting technology doesn't create these interferences with the quantum dynamics, and we could build a scalable quantum computer and change the world. But working on a government product, contract, I realized lots of bureaucracy. I was working with a lot of groups that weren't physically near each other. The academic community wanted to do experiments and write papers, but didn't necessarily really want to build it. They didn't have experience building large-scale technology. I came to the conclusion after 3 years, this needs to be a private effort. We're going to hire the best physicists, mathematicians, computer scientists, engineers in the world, put them all in one place, raise the right kind of money, and do this right. And so one of the things I did, this is really important too, you've probably heard a lot in this conference, it's not enough to just have technical prowess. I was a physicist, I could do a bunch of math and physics, but the other things that were key to any kind of success in this is I have to be able to communicate. I have to be able to go out, give talks, convince investors to put money into this. I have to know how to make different groups with different understandings and get them to work collaboratively. So some of the things they were doing with you guys today in the groups, getting you to talk to each other and get over being shy, really important skill sets for doing anything that matters in the world. And so the other thing I did is I started reading about companies that were doing big things that were having successes. So Celera Genomics, there was a big international consortium to try to, the Human Genome Project, billions of dollars over maybe decades to try to sequence the full human genome. Then you had Craig Venter, $300 million, 3 years, did it, right? By putting a very focused team with the right kind of culture and the right kind of technology and the right kind of push. You can see, SpaceX. There's a company now at doing fusion reactors in Canada called General Fusion. So I looked at what are the characteristics of the people who get things done. One was that they had a shared vision. They were purpose-driven and not profit-driven. Do or die. They're willing to take big risks. When I was at TRW, if you had a project that didn't work, I'll just go work on some other project that's some government contract the taxpayers are paying for. D-Wave, we're not successful, we're out of business. It's very motivating. Attracts the best people in the world who really want to get something done. Rapid prototyping. You can't take a long time to get results or you're not going to maintain your financing. Leveraging the best existing resources. The superconducting field for decades had languished, wasn't meeting its promise because people couldn't routinely build good circuits. So I said, well, who builds good circuits? The people who build your cell phones and the people who build Intel processors. I went to a place called Cypress Semiconductor. I hired a bunch of semiconductor engineers, taught them all about superconducting circuits and how to build them. And in 2 years, we bypassed everyone else in the world building those kind of circuits by getting the right people who already knew what they were doing. You have to be nimble, which means as you learn, you need to fail fast when you have an idea. Failing's fine. You just need to recognize it and change your strategy, move on. And being lean and creative with limited resources. Sometimes having too many resources is not a good thing because it can squash creativity. The other thing is to build an ecosystem of really powerful partners. So we talk to a lot of people right now. We have systems at Google and NASA, Los Alamos National Labs, USC, that are dreaming with us, and they said we want early versions of this so we can start understanding this technology, how to use it, how to build applications. This has been really useful because as we get information from them about using our processors, it informs our next designs. I'm not going to go through the physics today, but I'm just going to show you some cool pictures now. There's that ring, and on the right, you see what we call our unit cell. This is a chip. What we did is you go, where's the ring in that chip there? Well, what we did is we took that ring, we squashed it, and we stretched it. So see those lines going horizontally and vertically? Those are long, skinny qubits where current can go this way and the other way simultaneously. Where they cross, they can interact and talk to each other. And all this stuff in between is a whole bunch of really complex superconducting circuitry to control this thing, to program it, to read it out, to evolve its quantum dynamics. And you can see it looks kind of like a neural net, which doesn't hurt when you're trying to learn. That's the chip in package, the most advanced quantum processor on the earth right now. Now, remember what I said. We have to close the windows of the library. I have to isolate this system from all the environment so that these quantum dynamics and all the branches exist and can talk to each other. So you can see there the chip. It's on a holder. We have a bunch of exotic materials and oxygen-free copper and gold, because even fluctuations in the materials themselves can ruin the quantum dynamics. You can see there that now it's in a little box. You see that little cap over the top, a radiation shield. You can see layers and layers of radiation shields over all of that stuff to keep out infrared radiation, ultraviolet, signals from cell phones. And then here's another interesting problem. So let's say I have this quantum processor. I have to tell it what to do. That's an external interaction, right? Isn't that going to ruin things? So I'm going to quote Seth Lloyd, one of the kind of great figures in quantum computing. He said, when you talk to quantum systems, if you don't want to ruin their quantum dynamics, you have to talk very softly. So you have to have just the right kind of signals to steer the quantum dynamics and tell it what to do without ruining the quantum dynamics, and that's a trick. This is a system to get it to ultra-low temperatures, because that ring sits on a chip, and I don't want any wiggles. So all of that infrastructure there is to take it to 20 thousandths of a degree above the lowest temperature possible in nature, which is absolute zero. So just 20 thousandths of a degree above absolute zero. And then finally, you see it there packaged up. And this is something called a dilution refrigerator. And by the way, that refrigeration system works by using quantum fluids, things called superfluids. So if you take a superfluid and I were to spin it in a glass and set it down, it would never stop spinning. There's no viscosity in the fluid whatsoever, and another quantum dynamical effect. And finally, you can see it's in this big box, another set of radiation shields. And the only power really that's dissipated is not on chip, but just to keep the pumps going, to keep everything cold, about 15 kilowatts. And no matter how big you build this thing, it'll stay at 15 kilowatts and won't be something like 400 megawatts. We have systems like this. Google and NASA combined, and they created something called the Quantum Artificial Intelligence Center. And here you see over here at USC and Lockheed Martin have a collaboration with one of our systems. And I'm going to give you just I can't go into the details of all the machine learning stuff, but I'll give you an idea. If you talk about, say, neural nets, so some of you may be familiar with neural nets. This is one thing Google's interested in. You have neurons in your brain, and they're connected in very complex ways. And when you're a child and say you're learning language, what's happening is, as people talk to you and correct you, your neural net is evolving, and the connections between those neurons are getting stronger or weaker. And eventually they evolve to a point where you can understand what I'm saying to you, okay? People are building artificial neural nets where they have artificial neurons. Here's a neuron. It has a bunch of inputs and an output, and you can have like little knobs on those inputs, change how strongly it couples to other neurons. And so one of the things that's really hard to do with neural nets, to get them to do intelligent things like understand natural language, or maybe have a neural net, understand, a bunch of cancer research and find fundamental insights, or get insights on big data for some of these complex systems. It's really expensive to train neural nets. Out of all the ways you could connect a neural net, what's the best way so you get the least error and the best model of reality? So as soon as I say that, there's lots of different ways you could do it, but there's one way that's the best. This is one way we're using our quantum computer, because instead of doing one thing at a time, we can look through a vast number of possible configurations, and we can find the configuration that behaves the best in terms of understanding data or having the function that you want. So this is a big boon to machine learning if you want to use that to make better decisions on big data in these complex systems. And there are people now using this to explore bioinformatics, pattern recognition, protein folding, all that kind of stuff. I don't know how much time I've got. I'm not going to go through all of this. But there's an example of a neural net. Okay. So does this thing do what it's supposed to do? 5? Okay. Does this thing do what it's supposed to do? So D-Wave built this thing. The other thing you'll experience, by the way, if you try to do something impossible or new, is you're going to have a lot of critics. So when I left the academic field and I left the big government programs and we built our own company and we started having these announcements of quantum chips, people said, there's no way you could have possibly be this far ahead of everybody else. We don't think it's really quantum. Maybe you built some kind of special purpose classical thing, or maybe it has a little quantum. So since then, there have been a lot of tests. This is one of them that Google did. And Google said, okay, I'm going to build a maze. So think about it. This is a simple way of thinking. I'm going to build a maze, and there's a lot of walls in the maze and lots of ways to get through it. And we're going to take a Google data center and run millions of cores. I think they ran 2 or 3 million cores in a major data center to get through their maze. And it took them a certain amount of time. Then they took the D-Wave chip and they said, you know, if that D-Wave chip does what you says it does, and it can tunnel through walls, appear on the other side of walls, or explore lots of different possibilities, should be faster, right? It was 100 million times faster. So this came out in Tech Times and Hacker News and all that. You can see that D-Wave 2x, 100 mil times faster. Now that wasn't the end of the story, because this was a problem specifically designed to show the physics and not a commercial application. But this is kind of a cool, this is Hartmut Neven, Director of Engineering and AI at Google, we worked with for years, and he said a cool thing. If you remember the Wright Brothers, right, that built the first aircraft that flew, he said that this demonstration, it was like the early Wright Brothers plane barely got off the ground, but it foretold a revolution. The airplane took a trajectory through the air, and even though it wasn't faster than a horse, it flew through the air. It did something no one had ever seen. And what he said of this demonstration was that the D-Wave processor took a trajectory through parallel universes. It is literally that. The thing flew. And that's the data, by the way, showing D-Wave and the Google data center. We've applied this to a vast range of problems with a lot of different customers. Where we're going now is we want to expand the capabilities of this processor, make it easier to use, make it practical for large-scale problems, specifically, and a lot in machine learning and looking at big data. We built an infrastructure so people can interact with this over the internet. This shows kind of the rate of progress. You know, we don't have processors that after 24 months are 2 times faster. One processor generation, we went from 128 qubits to 500, and it was 300,000 times faster. Because these things don't just get like a factor of 2, say like Intel every 18 months. We've been on something like a Moore's Law-like trajectory, where every year we've doubled the qubits, but we don't just increase qubits. We change the way they're connected, how quantum dynamical are, less noise, more powerful, more precise. And so I'm going to leave you with a quote. When I was in 7th grade, somebody was asking me, like, how did I get into all this stuff? Why did I get into physics? There are moments in your life, reading a book, being at a lecture, having a conversation, that can absolutely change your life. So if you're walking by somebody's table and you see an interesting book, ask them why they're reading that. In my case, in 7th grade, I read a book by a guy named Paul Davies called The Forces of Nature. And in that book, he talked about electron being in 2 places at once and all this weird stuff. And it changed my life. I read that chapter over and over, and I said, whatever this is, something behind this curtain of my experience is a vast reality that I want to know and I want to play in. And so here we are, and I want to use a quote by Paul Davies to finish this. That the 19th century was known as the machine age. The 20th century will go down in history as the information age, and I believe the 21st century will be the quantum age. So thanks.
This was awesome. Okay, we have a bunch of questions. I don't want to be super pressed for time, but if you really have a burning question, we'll let you ask one question. There's the most enthusiasm right there.
Right.
Yeah.
Yeah, well, so that's a good question. So in parallel computing, right, what you're doing is you're taking a bunch of commodity processors and putting them together, right? So the best you can possibly do, let's say if I have 10 processors, you're 10 times faster. A million processors, a million times faster. Now, it actually turns out to be much worse than that, because if you talk to people who run supercomputers, they'll say that the typical efficiencies to parallelize a problem, best case 10%, because you can't, it's hard to move the data around and all that stuff, and a lot of times it's 1%. So let's say if you take the Chinese computer Tehani, 3 million cores or something. Well, what's 10%? 300,000x, right? But the problems that we want to solve blow up exponentially. So it's like you have a parallel computer thing that grows linearly and not even that good. You'll never be able to address problems at scale that scale exponentially. There's even mundane problems like, say, FedEx. How do I route my packages? What's the routing strategy I use to minimize fuel consumption? No one can do that problem at scale. They do approximations. It's better to use a computer than not, but there's nowhere near the optimal solution. How do you optimize a financial portfolio to minimize risk? Nobody can do that, because all of these problems with 500 variables, 1,000 variables, have an astronomical number of calculations. The quantum processors, in the best case, scale exponentially. So every time you add 1 qubit, you double the power of the computer, in the best case. Now, there's caveats to that for real-world quantum computers. But the idea is that only by accessing this exponentially growing space can you have a hope to solve these parallel computing and never get there. If you took all the matter in the universe and built it into a giant computer the size of the universe, you can't solve those problems. But quantum dynamics, what they call the Hilbert space or the multiverse, blows up exponentially, where you can have 10 to the 500th different streams. Right?
So if you have any more questions, hopefully Eric will stick around. We do have to wrap up because we're kind of pushing it for time. Sure. But I really did want to thank you for being here. It was incredibly inspiring. I learned a lot, and I'm sure all of you appreciated Eric coming out and sharing his wisdom and sharing his thoughts with us. So, that was a lot of cool.